a man is 5 feet tall, so he's kind of a short man. I mean, being, over 6 foot, 6'6", taller than that, 5 feet is pretty short. But a 5 foot man is walking at a rate of 4 feet per second directly away from a street light, okay, which is 20 feet tall. Okay, so the street light's pretty tall. It's about 20 feet. And we want to know at what rate is the length of his shadow changing, and then is that increasing or decreasing? Okay. So the best thing to do with this one is that we have to draw the image to start. Okay. And there's my drawing. So the light post is 20 feet up in the air. He is 5 feet. Okay. Now this is the tricky part. So the distance between the light post and the man, I'm going to say, is x. The distance of his shadow is going to be L minus x. And the entire distance is L. Now what we want to find is we want to find the rate of change in which his shadow is changing. Well, since his shadow is L minus x, okay, that means that the rate of change would be dl over dt minus dx over dt. Okay. So once we find the difference between these two, we're able to subtract them, and that is the rate of change in the object. Now, the other part that we have is that we know that he's walking away from the light at 4 feet per second, which is actually our dx over dt. So our dx over dt is 4, okay, which is actually this part right there. Now, these images right here are actually similar triangles. And similar triangles are proportional. And since they are proportional, we can set up a proportion to find them. So the first one we're going to set up would be L minus x all over 5, or the length of the shadow over the height of the man, is equal to the length from the light post to the end of his shadow all over the height of the light post, which is 20. And now we want to find the rate of change of each of these, the change in each of these. And so what we'll do is that we'll just take the derivative. Well, since these 5s is 1/5 and 1/20th, we can keep those out front, which would be 1/5 times L minus x and 1/20th times L. Now these are simple derivatives. What's the derivative of L? Well, it's 1 times dl over dt, and the change in x, which would be dx over dt. And then we would have 1/20th times dl over dt. Okay. And now from here, what we're going to do is that we want to be able to solve, okay, for dl over dt, because that's the part that we need. We know what dx over dt is. It's 4, but we need dl over dt. So we're going to plug in this 4 and for the dx. And now we have 1/5 dl over dt minus 4/5 dx over dt is equal to 1/20th dl over dt. And now we're going to get all the dl's onto the same side, dl over dt's onto the same side, which would get us dl over dt multiplied by 1/5 minus 1/20th. Oh, we don't need this dx over dt because we've already got it there. Minus 1/20th is equal to 4/5. Okay. And then once we subtract these, we would get dl by itself, which we're going to do this up here. We would end up getting dl over dt. Once we solve for dl over dt, we get it as about 16/3. Okay. That's after we move everything around and solve it. We get about 16/3. Okay, because this is about 3/20ths, I think. get about 3/20, and then you divide it onto the other side. And so this is dl over dt, so we'll plug that in here. And so our answer is going to be 16/3 minus 4, which is about 1 1/3. And we are in feet per second. Now, is that increasing or decreasing? Well, it's increasing. If you think about it, if you're by a light post, okay, and you're right underneath it, do you have a shadow? If you do, it's very small. But as you move away, you'll notice that your shadow's getting longer and longer the further away from the light source you are. Okay, and this goes along same thing with, it's just light rays and how they work, and if something's blocking it. And so this would be your answer for this one. All right, we're going to be looking at, let's say we have a cone that's holding water, okay? And what's happening is at the bottom of this is like a drain, and it's slowly draining out water. And it's only draining out about 4 cubic feet per minute, and we've got a cone, it's about 10 feet tall, and it's got a radius of about 3 feet, okay? So that means since it's draining out about 4 cubic feet, that means our dV over dt is equal to minus 4. Okay, our h is 10, our r is 3, and it wants to know how fast is the surface falling when it's at 6 feet. So we want to find our dH over dt at when h is 6. Okay, so that's what we're going to be trying to do. And the first thing we have to do is trying to find, okay, well, what's the relationship between the radius and the height? Because we don't care about what the radius is. All we're worried about is the height. Well, the radius over the height is equal to 3 over 10. Okay, and since it is a cone, it's got that same ratio all the way down until the bottom. And so if we were to solve for r, we would get 3/10 h. Now that 3/10 h we're able to plug in for r wherever we want. And so now we're going to be using the volume. So volume is equal to 1/3 pi r squared h. Okay, we're going to be plugging this in for r, this whole thing, in for the r to solve it through. Which means we have v is equal to 1/3 pi 9 over 100 h cubed. Okay. Keep multiplying it all the way through. We end up getting v is equal to 9 pi over 300 h cubed. Okay. Now we take the derivative because we're given the rate of change, which is minus 4. So we know that dv over dt is equal to, it looks like about, we drop the 3, giving us 9 pi over 100 h squared dh over dt. And now we're going to plug in that negative 4. So it'd be negative 4 is equal to 5 pi over 100. And so we plug this in for there, and then we're going to plug a 6 in for the h, which would be 36 dh over dt. Solving for dH over dt, which is the main thing that we want right now, that dH over dt will be approximately negative 100 over 81 pi. And the units for this would be feet per minute. Okay, feet per minute. Okay, so there's our dH over dt. Pretty straightforward, pretty simple going through. And that's actually our answer for the first one. Okay, so that's our answer for the very first problem. Okay, so as it's being as the water's being let out, when it's at 6 feet, it's actually falling at negative 100 over 81 pi feet per minute. That's the rate in which it's falling. So the next one's asking how fast is the surface area decreasing at this instance. Okay, and so what we're going to do is now we're going to do surface area. Well, since we got a circle, we're going to use pi r squared. Pi r squared. And since we know what h is, we know what dh is, we don't know what dr is specifically. So we're going to put the h in for this r. So that gets us a is equal to pi times 3 over 10 squared, which gets us a is equal to pi times 9 over 100. 9 over 100. Oh, and then there's an h, so then it's h squared also. And now we're going to take the derivative because we want to know what the change is. How fast is the surface area decreasing? So we want to know what dA is. So dA over dt will be the derivative of this, which would be about 18 pi over 100 h dh over dt. We know what h is. H is still 6. And our dH over dt is that right there. And so now we will plug in all that stuff to find what dA is. So dA over dt is equal to 18 pi over 100 times 6 times negative 100 over 81 pi. Right. And then we will simplify the rest of the way through. And we end up getting our dA over dt. If you were to multiply, the hundreds cancel, the pi's cancel, leaving us with 6 times 18 all over 81 negative, would get us a negative 4 over 3. And then our units for this one is feet, and since we're dealing with area, we square the feet, and then it would be the unit of time, which would be minutes. So the change in the surface area at this time would be, it's decreasing by 4/3 of a square foot each minute. Okay, and so again, this is dealing with your rates and related rates and how to, basically we're taking something that we have multiple variables, turning it all into one variable so that we can solve it. And then find the rate of change, which is using the derivative at that point. Alright, so what we're going to do now is that we're going to be looking at one with a train. And so we've got a train, all those, a train from Albuquerque leaves at this time, and a train from New York leaves at this time, what location are they going? We're going to do something like that, just cooler because it's calculus and not just algebra. And so a train starting at 11 a.m. travels east. So we've got a train traveling east at 45 miles per hour. So I'm going to call this train DE, or I'm going to call this train E. So the DE over DT will be 45. Okay. And then another train starts at noon, leaves from the same spot but heads south at 60. Okay. And that one I'm going to call DS over DT. And that's going to be 60. Okay. All right. So now, how fast are they separating at 3 p.m.? Okay. And so what we have here is that we're making a nice little right triangle. And what we're trying to find usually we like saying distances is d, so I'm going to say what's dd over dt. That's what we're trying to find. And to find the distance in a right triangle is Pythagorean's theorem. A squared plus b squared equals c squared. So using our variables, it'd be s squared plus e squared is equal to d squared. Okay? And so now, if we want to find what dd over dt is, we got to take the derivative of each of these. So the derivative of each one of these in respects to time would be ts ds over dt plus it would be 2e dE over dt is equal to 2d dd over dt. Okay, and now we would want to get the dd over dt by itself. So dd over dt is equal to s ds over dt plus e dE over dt all over d. Okay. Now, let's plug in our numbers. Well, what we have to find is okay, well, what is S? Well, S is the one that's heading south. How far has it gone after at 3 p.m.? Well, it started at noon, so it would be, from noon to 1, and then 2, and then 3. So that's 3 hours. 3 times 60 is 180, so it's gone 180 miles. And now the other one has gone 45 starting at 11, so 11, and then you go 12, 1, 2, 3, that's 4. So that means E would be 4 times 45, which is also 180. So they've gone the same distance, okay, just in different directions. Now that's our E, and that's the other one, E and S. So now we can start plugging all this stuff in. So we'll have 180 times 60, which is what ds over dt is, the speed of the southbound train. And then it would be 180 times 45, which is the speed of the eastbound train, all over d, which is the distance between the two. So we're going to be using our distance formula, which would be the square root of 180 squared plus 180 squared, which is equal to dd over dt. And now from here we'll simplify, condense everything, put it all together. We end up getting something close to about, the top ends up being about 18,900. The bottom is about 25.4556, something like that. Approximately, somewhere around there. And that gets us about 74.246 as our dd over dt. Okay, and this is our speed in miles per hour in which the trains are separating. So every hour at that moment, they're actually gaining 73.246 miles per hour. Okay, at that moment. So again, this one was just kind of setting up, seeing, okay, well, it makes a right triangle, and then identifying the distances from there. Okay, so those are your trains.